this video, we'll solve some problems related to the Wittig reaction. So our first example will be to complete a mechanism and draw the product for a Wittig reaction. We will start with benzaldehyde. So we have a benzene ring bonded to an aldehyde group. And then we will have an ester ylide, so an ylide with an ester group. We showed the formation of this 2 videos back. And I'm going to draw it in a convenient way to show this reaction. So the carbons will be lined up with each other, and the phosphorus and the oxygen are lined up with each other this way. And that will be helpful for the reaction. We have triphenyl phosphorus. Phosphorus has a positive charge. We're showing the ylide with the negative charge on carbon, positive charge on phosphorus, and then the carbon is bonded to an ester group. So what we have so far is an aldehyde and an ylide. So we can go ahead and show that 2+2 cycloaddition mechanism, where we have carbon to carbon bond forming, arrow starts at electrons, and then oxygen to phosphorus bond forming, again the arrow starts at the electrons in the pi bond. So this is that 2+2 cycloaddition. I'm going to draw the 4-membered ring first. So we have a carbon to oxygen, we have a new carbon to carbon, carbon still bonded to phosphorus, and then the new oxygen to phosphorus bond. So that's our 4-membered ring. The carbon in the top left corner, that was the aldehyde carbon, so that's still bonded to a hydrogen and a phenyl ring. The carbon in the bottom left corner of the 4-membered ring was bonded to that ester group. And we didn't show, but it is also bonded to a hydrogen. That's still present, just wasn't shown in the starting material, but I'll add it in there. And then the phosphorus is bonded to the 3 phenyl rings, so PPH3. Okay, so here's our 2+2 cycloaddition product, and then now we form the carbon to carbon double bond and the phosphorus to oxygen double bond. So carbon to phosphorus electrons in that bond form the carbon to carbon bond. Carbon to oxygen electrons, which are held closer to the oxygen atom, will then form the oxygen to phosphorus bond. And then we have formed our product. So let's draw the carbon to carbon pi bond molecule first. So we have a new carbon to carbon bond. We'll draw this here. Carbon to carbon. The carbon on the top is bonded to a phenyl ring and a hydrogen. Carbon on the bottoms bonded to a hydrogen and an ester group. And then the phosphorus and oxygen product is the same for all Wittig reactions, triphenyl phosphine oxide. Now if we look at the product here, this is an alkene, and here we have formed the E-alkene. This is what I've drawn, where our high priority groups for the carbon on the bottom, that's the ester. For the carbon on the top, that's the phenyl. So these are our high priority groups. They're on opposite sides of the pi bond. So that's the E-alkene. When we have bulkier groups, only the E-alkene forms. So for this reaction, we have a phenyl ring, which is pretty bulky, and that ester group is pretty bulky. So for this reaction, only E-alkene forms. With smaller groups, both can form, but E-alkenes are slightly more thermodynamically stable. So they form generally in a higher concentration. We can also think about the 4-membered ring. It would be difficult sterically for the priority groups on the 2 carbons, so the phenyl ring and the ester group, to be right next to each other. They're bulky groups, so they're going to be far away from each other as much as they can, and so that results in the E-alkene formation. All right, let's do another example. We will complete a multi-step transformation. So we will start with, let's see, 5-membered ring bonded to a phosphorus with 3 phenyl rings, and the phosphorus is positive. In the first step, we will be adding butyl lithium in, let's say we're adding it in hexane. This will form a molecule. We'll figure out what that is. And then we will add another molecule. That will form 2 molecules as the products. Okay, so let's talk about what will happen here. We notice the first reagent here is butyl lithium. Butyl lithium is a strong base that will remove a hydrogen from the molecule that is added. We look at the molecule that we're starting with. We have a positive phosphorus, but we don't have a negative carbon. So this carbon, that indicates that this carbon has a hydrogen here. If it's not charged, it must have 4 bonds. So we add the butyl lithium to remove that hydrogen. So butyl lithium removes the hydrogen and puts the electrons in that carbon to hydrogen bond onto that carbon. So I'll draw the mechanism. It's just a 2-step mechanism. Carbon to lithium bond. Take the hydrogen electrons, the electrons in the bond go to the carbon atom. So this also forms butane and this, not lithium hydride, but lithium with a positive charge. Hexane here, this is our solvent. So hexane solvent, butyl lithium, removes a hydrogen, and we form the ylide. So we still have our positive phosphorus, and now we have a negative carbon with a lone pair of electrons. So that is the ylide. So first step, forming the ylide. Second step, now we've added this reagent here is an aldehyde. So we have an ylide that we produced in step 1 in the presence of an aldehyde. So this will do a Wittig reaction. The ylide will react with the aldehyde. Now, in this reaction, we always form triphenylphosphine oxide. So let's write that in, triphenylphosphine oxide. So that is that triphenylphosphine oxide, that's where the atoms, the phenyl rings, the phosphorus, and the oxygen end up in triphenylphosphine oxide. The remaining atoms, so the carbons and the hydrogens, form our alkene product. that carbonyl carbon is a carbon in that carbon-to-carbon double bond. So we can just rewrite this like this. We removed the oxygen. That's part of triphenylphosphine oxide. The carb anion in the ylid, so looking at the ylid molecule, the negatively charged carbon is what forms a new bond to the carbonyl carbon. And that new bond is a pi bond. So we can show that now we have our 5-membered ring, that carb anion that's part of the 5-membered ring has a double bond to the carbonyl carbon from the aldehyde. So I didn't draw out the mechanism, but you could pause this and try writing out the mechanism using the ylid mechanism, the 2+2 cycloaddition that we've talked about, and make sure you're getting the same final product. We'll do one more example here. We'll say we'll draw an ylid and an aldehyde or ketone to form a product that's provided. Okay, so here's our desired product, and we need to draw an ylid and an aldehyde or a ketone. Okay, so let's remember when we are doing a Wittig reaction, the new carbon-to-carbon bond occurs between the carb anion in the ylid and the carbon in the carbonyl group from the aldehyde or ketone. So we could look at this final product and picture, let's see, I'll use gray here. Imagine this bond kind of being split there. Well, that tells us that one of those carbons was from the ylid in that double bond, and the other was from the aldehyde or ketone. So let's say the left side is the ylid. We'll use this purple color for the ylid. Well, the carbon that's part of the pi bond must have been the carb anion that was bonded to phosphorus. That carb anion had to also have bonded to a methyl group right here and an ethyl group. So we have a methyl group and an ethyl group. And that phosphorus is always bonded to 3 phenyl rings for the ylid. So now let's say the right side was the aldehyde or ketone, right side of that pi bond. Well, that means that the carbon that's part of that double bond must have been bonded to the oxygen in the aldehyde or ketone, and then that carbon is bonded to the phenyl ring and the methyl group. So we have our ylid and we have the aldehyde and ketone. In this case, it's a ketone. Now, this is one way to produce this product. Another way is to say, we'll use some different colors here. We're still splitting the molecule in the way that we have shown it here. But now let's say, because once we're looking at the product, we don't know which of the 2 carbons that's part of the pi bond was from the aldehyde and which was from the ylid. So let's say the left side was the aldehyde or ketone. And the right side, color can I use here? We'll use orange. We'll say the right side was from the ylid. Well, then the ylid carb anion is the carbon that's part of the pi bond. That is bonded to the phenyl ring and a methyl group, and then that must have also been bonded to a phosphorus with 3 phenyl rings. Then if this were added to a ketone, where now this carbon right here was the carbonyl carbon, then that carbon was bonded to a methyl and an ethyl group, and here's the ketone. So both combinations, this combination of ylid and ketone would produce this product. This combination of ylid and ketone would also produce this product. We have a new carbon-to-carbon pi bond forming in the same location. I guess not in the same location, but this would produce the same final molecule, just the carbon chains coming off of the carbons that are part of the pi bond can come from the ylid or from the ketone. As long as you're matching up those groups properly, you'd form this final product. Again, you could try working through the mechanisms, making sure that you're getting that same product as you're drawing out the full Wittig reaction. But for this video, we'll end it here.